Hello, I'm Chris Thanis. I'm a KMP developer. Tech support's coming out. He told me Tuesday, probably Tuesday afternoon. I'll try and be here this time. Yeah, we're getting into how to program from the ground up, and we're getting to high level languages now. This is the fun stuff. The big idea was okay. So went to assembly. It's like monogamous. Well, can we do some more? Can we make it a little easier somehow? I don't know. Somehow, can we make this not so bitey and more portable so we can go from machine to machine? When I leave this institution of higher learning, I can use it at a different machine. So the high level meaning it's more friendly for humans to work with, not necessarily more powerful or faster. Probably usually not faster. So what it means, like high level, it's like low level is the bits and bytes, and then the hex code is a one up from that, and then one up from that is the mnemonics. Well, can we do another level up? Can we put another level up so we don't? Can you have some way of abstracting that stuff away? So if I'm on this CPU, it runs this. It'll compile to this machine code. If I'm on this CPU, it'll do this machine code, or just make it easier somehow. Can we experiment with that? And they certainly did. And it was a more abstracted, general purpose, portable assembly language. But no matter how sophisticated these languages are, it always compiles down or gets down somehow into the machine code language instructions, and then those are actually run. So these languages are still always running down in the binary in opcodes and assembly language instructions, and it's just these ability for these compilers to compile down the assembly language instructions, which turn into machine language instructions, which turn into the stuff that actually runs. So that's where that's coming from. So the first programming style. So let's get into the programming style. So there's different styles of programming. Oh, really? Okay. Well, the first one didn't really have a name. It was just programming, but it was imperative. That means you told it every single step, every single thing you had to do. You had to tell it. Like machine language, that's where it came from. So the first, we got a little away from it a little bit with the call and go, return stuff. We're doing subroutines. Got a little bit of the machine language kind of folded in some stuff, but people are still using GoTo a lot all over the place because it's just much easier to deal with and understand. There wasn't a lot of like education around this stuff. We were just making it up as they went. So there was a big push to make a program that everyone could use and get used to using computers and like experiment with these things. So I want to show this a couple different things about BASIC, which was beginner's all-purpose symbolic instruction code. It was extremely influential on computing, especially in the early days. If it wasn't for BASIC, all that microcomputer stuff would have never blown up because these things existed for a couple of years. Those little bit twiddling different kinds of computers, which had the hex output, just like how Ben Eater's making. There was a whole bunch of those for like 3 or 4 years, but no, they didn't really catch on until BASIC. So BASIC, if it wasn't for BASIC, we would not have any of these computers. We would not be working on these things this way. There was eventually someone's going to come on like it, but BASIC was the one that did it. Let's get into it.
Back then, people really didn't have an idea of what a computer was. They would see maybe movies or TV where there would be a big computer in a room with lots of flashing lights. They call it a UNIVAC or an IBM.
That was like the 50s.
And the idea that a person could just go and program one was completely foreign.
I mean, think about it. You'd have to wire all that stuff up. Just think about Ben Eater. You'd have to be doing all that stuff. It's like, there's no way unless you went down into it like we are and then following along and super into all where just happened to be at the universities where they were exploring this. Other than that, you're like, no way.
Kemeny was brought to Dartmouth to revamp the Dartmouth math department. And when he was chair, one of his first hires was Tom Kurtz, who he had met at Princeton. Kurtz, in his many trips to MIT, which had, I guess, the closest computer actually to be used to the Dartmouth campus, Kurtz learned about something called time sharing.
Before time sharing, people used batch systems. And what they had to do was either create a deck of punch cards using a key punch and feed them into a hopper, or there were other input devices such as paper tape. Before that, people actually had to flip switches.
Time sharing gave the ability.
Flip switches. No, thank you. There's the switches, by the way. There's the lights. There's the switches. We're going to toggle in. Oh, so tedious. Error prone. So not only did you have to type it in, they had to check it and check it again before you went to the next one because you just got one wrong. You don't know which one. Good luck.
for many programs to be executed in a reasonable amount of time as
Okay,
opposed
that's right.
To flip switches.
Time sharing gave the ability for many programs to be executed in a reasonable amount of time as opposed to programs being executed one after another. Kemeny, on the other hand, was very concerned that people should have a reasonable language with which to actually speak to the computer.
Okay, we'll look at the time sharing thing in a second, but the language is important.
To get their ideas implemented and executed.
What BASIC did was it really democratized computing along with time sharing. So now people had access to computers because of time sharing, and they could write their own computer programs because of BASIC.
May 1st at 4 a.m., that 2 programs were executed simultaneously, both written in the BASIC language, and so that marriage of simultaneity and simple language is the birth of BASIC. When it was introduced in its original form, was used on the Dartmouth
Simpler. Not simple. Simpler.
campus by students, faculty.
A bunch of kids in the high school started writing programs using the time sharing system that Kemeny and Kurtz had developed and made available to the local kids and eventually to high school kids all over the country.
Okay, I want to just pause here for a second for a cameo by the one and only Bill Gates. Yes. If it wasn't for this kid playing with this computer at this age, the computer revolution would have never happened, because he was the one that brought a version of this thing he'd been using to IMSI, who then created a basic, he actually created a basic interpreter, which we'll get into in a second, that ran on it, that made the computer super popular. Couldn't even keep it in stock. And and the only reason why that took off, because there's plenty of other ones like it, was because Bill Gates had been using this terminal here when he was this age.
At least 85% of all students had done some form of programming, which, remember, we were on a liberal arts campus, and that's kind of extraordinary. Not only had 85% of the students written 4 programs, but that 90% of those programs were correct. So that's
Well, it's not that unusual, because it's, a liberal arts. This is liberal arts. Computing, once you get past the hardware engineering stuff of it, it's all, what does this mean? What do you mean by that? How are we going to do this? What's important? What's not important? It's all like social stuff. It's so crazy. People think it's this machine and there's bits and bytes. It's like, yeah, that's kind of the surface level. It is cool. I like it, but that's not what the job is.
an even more staggering statistic.
The college kids would bring their dates to the computer center. There was a program called Date *****. That meant it was in the public library, and you would sit there with your date. I mean, not that I had a date at that age, but they.
Oh no! Don't even think. You had a date. His right hand.
Come in with their dates, and they would answer questions.
I shouldn't say that. That's wrong.
And then it would print something out.
The undergraduates built time sharing at Dartmouth. They quickly became actually national experts in time sharing.
Once people have computing, they come up with all sorts of ideas. We certainly see that today, and it started really with BASIC back in the 60s.
I
Oh
think
yeah.
it's honest.
Oh yeah, it exploded. It totally exploded. And we're gonna get to a little more of the time sharing thing. Where was that thing? What is it? Is this it? Yeah, let's go to time sharing. Let's talk about it.
At one point, I can remember being down at MIT. I was still going down to MIT once in a while. John McCarthy, famous in artificial intelligence, had been at Dartmouth.
Okay, by the way, this John McCarthy was the John McCarthy in that movie War Games. Like the guy the scientist guy. It's this guy. He's totally this guy.
He went to MIT because they had better computing facilities at the time that he went. And he said, you guys should do time sharing. Okay. Now, what was time sharing? So time sharing was an idea. Instead of running one job to completion and then putting the next job in, was a way of running one job for 1 second and then doing something so that the next job can get in, running it for 1 second, and the next job, the third job for 1 second. Shoot. In this way, if you had a small job, you could get the results quickly. And if you had a big job, you had to wait, just as in the old days. Well, all we had was the LGP30 at the time. We can't do time sharing in the LGP30. It's just too small
That's
a machine.
the previous batch computer.
The input-output is just too difficult. So I came back to Dartmouth and I talked to John Kemeny and I said, John McCarthy thinks we ought to do time sharing. So Kemeny said, okay.
Well, at some point,
Okay, so that's what time sharing is, just splitting the computer up between a bunch of different people. So it made it possible. It made it possible for, instead of having one person sit at the machine and have it do its program, we're splitting up the machine into tiny little slices, and each person gets a tiny little slice of time. We could hook up a whole bunch of terminals to this thing. They figured that out. That would just go between all the terminals. It would remember which terminal it had and which one it was talking to. That's how it worked.
In the fall of '64, we were invited to make a presentation at AFIPS. It was a big deal of computer people in San Francisco. There was a room of maybe 2,000 people in the room. We hooked up the acoustic coupler on with the handset, and
So that's a phone line, an old timey phone line that's hooked up to this acoustic coupler, which all it does is took the sounds of the electronic sounds of ones and zeros and converting them to digital ones and zeros that were just line pulses. That was this standard called RS-232, which is this little plug right here, and that plugged into a simple, dumb, old timey terminal, TTY teletype terminal. And that's how they shared the time. It was over phone lines.
And we linked the Model 33 teletype to Hanover. We got the dial tone, and all of this was.
That's a TTY. It comes from this thing. this old ratchety. And it's got paper tape input and output on it. Also, way before computers. This is all how they talked back and forth across phone lines across the country when they're typing. Justin. Is that machine? Is this thing?
All this was videotaped on the screen for the audience, and we were entering programs in it, and lo and behold, out comes the answers and shown on the screen, and everybody went bananas on this simple, basic language being compiled and run in San Francisco over ordinary telephone lines and the computers in College Hall in Hanover.
Yeah, extremely revolutionary. Completely blew people's minds away. Now it's like, okay, yeah, so why is that big deal? Well, before that, you'd have to be in the room next to the computer or have one line to the computer, and you were the only one talking to it. And it was expensive, and you better be important. You better be doing something real important, because there's like 15 people behind you that want the time of the machine, and you're holding things up, buddy.
And we were bombarded with questions of what it was. And that's the first time I really got to see the impact of what the Dartmouth time sharing had.
We had taken a fairly expensive computer that could only be used by one person at a time and converted it into something where it wasn't just 30 users who could use it, it was 30 undergraduate students using.
Okay, this program right here, you could take today, which I'll show you a little bit later. You could type this program in today and it would work. And you could read what it is. Can you see what this program does? Here's the line numbers. It defines a function of x. So you bring in x and it calculates this out and gives you an answer. So read n. Okay, so you type in a number. It defines some variables. It does a little loop here. There's your go-to, the deadly go-to. Oh my God, no. And then, yeah, I think he's got a little error here, but that's okay. Because he's got the loop here. He doesn't quite understand how this works. But that's okay. He's a student. He's going to figure it out. Watch. But that you could type this program today. You could find out what the bug is.
Computer simultaneously writing programs, getting answers quickly. It was a combination of immediacy and simplicity that had not previously existed.
I know Kemeny was pushing everybody to, in their beginning math classes to do something with a computer.
Will be the solution of a quintic or fifth degree equation. This is particularly interesting because
If this had been built on a language like ALGOL or Fortran, instead of teaching students in 2 or 3 hours how to use BASIC, one would have spent easily a full week trying to have them understand ALGOL and Fortran. And a lot of
Exactly. That was the problem with these Fortrans and co. And even then, I mean, they had them on these timeshare eventually, but the whole point of doing the timeshare was for basic only. So they were like leaving Fortran. They're trying to leave Fortran and all those other ones behind and just do this just with the timeshare. And that's why it blew people's minds away, because all this stuff was so inaccessible to most people. Once they saw they could write a formula like that particular line right there made people's eyes go like this. What are you kidding me? And they're having the little for loop there to calculate the numbers, having to do that out by hand with a slide rule or no. The fact that you could do that, all the researchers look like this.
students with their best lost interest.
writing this program in BASIC is your next assignment.
So this was the first.
There, all those numbers printing out, they all just went nuts. They went, holy crap, are you serious? I don't have to do the slide rule. Instead of doing one calculation every minute or so, I can do 1,000 in five at the same time. People went crazy.
Setting large-scale effort in undergraduate education for computing.
Today, approximately 85% of all Dartmouth undergraduates make use of the computer. Students in more than 100 courses, ranging from the sciences and mathematics to economics, education and psychology, to languages and sociology, make direct use of the system in completing course assignments.
So we had many different faculty members in many departments who were doing more and more.
Instructor Waite is also using the computer in the study of Latin poetry and
He's
prose.
saving that. He's lighting this program right here. He's having to type it in every time. Instead of having to type it in every time, he's loading it on this paper tape here. And he's over a phone line over here somewhere. That's probably the modem right there. He's hooked up to the phone line. So he's doing it from his office. He doesn't even have to go in. He's like, give me the terminal. I'm typing all these numbers in. He's loading the program, saving the program, or loading his data. This could be his data as well. Because just all it is you press play on a thing and it just starts typing whatever's in there, or whatever's being typed from the other side gets put on the paper tape. So you got a record of everything too. It's crazy.
As well as preparing elementary exercises and beginning Latin.
He was doing stuff with Latin. So anyway, they had a whole bunch of people using BASIC for all kinds of crazy stuff that no one had even thought about before.
BASIC, the beginner's all-purpose symbolic instruction code, has been developed 1964 by people from the Dartmouth College and was supposed to be an easy-to-use programming language.
So here's Commodore 64 emulator, but you could just turn on any old Commodore 64 and it boots up. It'll boot up into this prompt here. All these like PETs, as TRS-80s, Apple IIs, they all boot up into BASIC. So it's ready to go right there. And that blew people's minds. Because before that, there'd be no display at all. It'd just be like, okay, you can start typing hex codes in. Even the Apple I didn't have BASIC in it yet. It was still just a monitor where you can type in hex codes. Instead of flipping switches, you could type in the hex codes. And that blew people's minds. And then when they could boot up into BASIC, that just threw people's heads way back. And that's why these sold millions and millions of units. It's because before that, it just wasn't accessible. Because the language was too hard. It was too complicated. This took all that crap away. Now, it was extremely limited in a lot of ways. And it was very slow. It was a lot slower. It was about 100 times slower, 50 times slower. 1/10, 1/50th, 100th the speed than doing it in assembly language. So you could do rudimentary text games and stuff, or, lots of different, but you can also experiment. And people were super fascinated with how this would work. And the scientists went nuts. They all got into it. And because it was so accessible. And that was the reason.
Its popularity especially rose with the boom of the first home computers in the late 70s and 80s. The whole operating systems of prominent home computers like the Commodore C64 mainly have been a BASIC interpreter. BASIC was Microsoft's first important product before the company released its first operating system, MS-DOS. Even MS-DOS and very early Windows versions came with a BASIC interpreter.
If you see a computer from about 1979 to about 1991, 92, just a standalone computer, if you turn it on, you can just do that program, or they could say anything from just turning it on. It was mind-blowing.
The C64, you could start programming right after the computer started. By typing run, your program would start. Execution is stopped with the escape key, and the code can be seen by typing list.
Here's MS-DOS IBM
you were
PC.
one of those happy people with a tape or floppy drive who were able to even store their programs. In MS-DOS, the basic interpreter QBasic can be used for programming. This interpreter can also be accessed from Windows. I hope you had some fun watching this.
Yeah, it's available all the
video.
So we'll get into that. We'll get into that a little bit. How far are we through? 18 minutes. I think I'm just gonna leave it there. No, we'll get to the procedural. Let me go take a little. Hold. I'll be right back. Okay, I think I'm gonna complete it with this next thing about batch programming, so we can do the contracts between batch and interactive. The basic stuff where you just boot up into the prompt and start typing in the programs is called interactive, because you can stop it, break it, edit it, run it, all right there. Versus batch. Let's get into the batch processing. What that looks like. Just to contrast it.
Computing and computers.
So this is the way things were done in the procedural style back in the day. This is called procedural style. Again, love these old movies, old videos, because definitely they show better, like in detail, how this stuff really works.
Come to the Royal Bank of Scotland to see how one of the major clearing banks uses its computers. Now, computers are important in banking. For example, on an ordinary cheque, there are numbers at the bottom of the cheque which are in a special computer format. And the bank uses these numbers in order to identify individual accounts.
So people used to use checks to pay money before everyone had debit cards. They used checks. They sent checks everywhere. So you give somebody a check, and they would then take that check to the bank, and it'd be reconciled to send the money to the account. And it was these little paper notes that people would write on. So when people thought about computers back then, they really did think about this batch thing. So the idea that these would be interactive, that I could type stuff in, was like, what? What are you talking about? So this is how people thought about it just before the interactive the basic stuff came on.
We asked Campbell Doherty, the manager here, about the importance of computers and how they've affected the way he deals with bank accounts.
Computers are very important to bank managers
This guy looks like a banker.
nowadays, and this due principally to the increase in the number of customers and the transactions passing through their accounts. When I joined the bank at first, all of these transactions were recorded in a ledger, very laboriously by a clerk, where he sat and posted the various entries.
So wow, the amount of technology change that this guy had seen from doing ledgers to hand-counted ledgers when he was a kid to how they're using computers now, like, whoa, blows his mind.
Debits and credits, bringing out the resultant balances. Now, of course, all of the information is contained within the computer, and it produces on our behalf and for the benefit of the customer statements on the transactions that they have carried out over, say, a period of a month. Such a statement as this, where we see the various debits that have come through the account, the various credits, and the resultant balances.
All this information, debits, credits, and so on, has to be held by the computer, and not just for one customer. The Royal Bank has about 500 branches throughout the country, and information about customer accounts at all these branches is now held centrally in Edinburgh by the Royal Bank's computer system. Here at the computer centre, information is processed to keep customers' accounts up to date. And what we're going to do in this programme is show you how the computer does it. We have to start by seeing where in the computer the information is stored. Here's our diagram of a computer's structure. The large amount of data has to...
Does this look familiar? Same stuff all the time. Same stuff. Backing store. Okay. Oh, backing store. You mean tapes and hard disks and RAM, memory. A backing store. No, that's not what it is. It's a backing store. People still use this today in like caching and like, we're talking about caching. This is where it came from.
To be kept in the part of the computer called backing store. It's held in backing store until it's needed for processing. The data is organized in files. A file is a collection of data needed for some specific purpose. There's usually more than one file in backing store, but we're going to concentrate
And these are stored on tapes.
on the single file which holds data about customer accounts. We spoke to the controller of systems development, Norman Irvin.
We use
And there's the tapes.
22 magnetic tapes to store the information about our customers' accounts. In the Royal Bank, we have 1.5 million accounts, so therefore, each of those tapes will contain approximately 70,000 accounts. This tape, for example, contains all the accounts for our branches in and around the Edinburgh area.
But just what information is stored?
So that one tape, you could fit all of those tapes, and all the tapes they ever had before then on one 1 terabyte hard disk. That's like SSD. That's like this big. This was like about what, a megabyte, 400K, something like that.
On this tape. It's information which is needed to produce a bank statement. Each line of the statement represents a single transaction, and the whole statement is just one record in the bank's master file. There's one record for each account in the master file. Let's see what a typical record might contain. The first item of data is the number. This number identifies the record, and it's based on the customer's account number. Next, there's the customer's name and address. And then details of transactions since the customer's last bank statement. For example, these two transactions were checks. On the 6th of December, there was a check for £450. The number underneath is the number of the check. The following day, there was another check, this time for £412. So there are 4 items of information on this record. The number which identifies the record, and then the name and address and the 2 check transactions. We call each of these items a field. So this record has 4 fields. Other records will have different numbers of fields because there are different numbers of transactions on each account.
They would use that name field now. They call this a record now. So the record would actually have all these elements or items in this or records inside this weather record. And those records would have the field. So the name, address, phone number, each one of those items. The name is a field, address is a field, amount transacted is a field. Those would be the fields. So they changed some of the terminology, and it's confusing, right? But they changed some of the terminology. You just want to know that.
When we put all the 1.5 million records together, we get the master file. And to refer to any particular record, we use the number in the first field. This number is unique to that record. In fact, the records in the file are stored in sequence, given by these
These are called IDs now. In database, we just call these IDs.
identifying numbers. A file ordered in this way is called a sequential file, and maintaining the records in this sequence is vital for the way the file is brought up to date.
The method we use to update our master file is batch processing. The new transaction information is collected into a batch during the day and is then used to update the master file that evening.
So we can therefore say that the updating process takes place on a regular scheduled basis, once every night. And when we update this master file, we don't physically change the file. Each night we create a brand new master file by copying the previous day's information from the master file, and in the process we include the new transactions in the new master file record.
So that what they're doing there is something, it's a style called functional program, where the data is always immutable. They're never mucking with the data, the permanent data that's being recorded. They're always making copies of it. So in the process of making a copy, they're updating and changing and adding and stuff all along. And all those updated changes have to stay somewhere else. And he talks about that, how they put these tapes together. It's very clever. It's very clever. It's also very time consuming, because somebody has to put on and dump these tapes all the time. Every night.
So records are copied from one tape to another, and in the process, the new transactions are added. Let's see what happens to a typical record during this process. File processing uses the computer's working store, so a copy of the record is made inside the working store. Now if there's data about a new transaction, this is added to the copy of the record. These copies from the working store are used to build up a new master file. But how does information for updating the file get into the computer? Most of the information comes from the bank itself, when customers transfer money in and out of their accounts. For example, cashing a check.
Thank you. Just like sign the back for me, please.
You had to sign it. Oh, like they're going to check. Okay.
We've chosen to watch a check being cashed, because this transaction affects only one customer's account.
How would you like your cash?
£40 and 5 and £10 and singles, please.
This transaction is to withdraw £50. So what the computer must do is debit the account by £50.
Here.
To do this, the check is taken from the cash desk into the terminal room. These terminals are connected to the bank's central computer. And this is where the information is typed in. Here's our check. And there's the debit for £50. Our transaction, and many more transactions input during the day, are stored, ready for the batch update process later that evening. It's now time for the operators to run the program which updates the master file. The program's name is Caustic.
Caustic. We're going to, like an acid, we will change the transactions.
CAU stands for Current Account Update. The program begins.
And there's that word job. That's where we get a lot of like parallel processing terminology from. Job.
By asking the operators to mount two tapes.
Mount this tape, human, for me. Go take out tape number 6 and put it on this thing. Put it on this thing. And those guys just scramble around all the time for every single tape for every single transaction. Ugh. Well, that's not really. I would not thought that's such a boring job. Pay probably well. This guy, that's what he does all day. He's like, ugh.
And second is a blank tape. For the
new He's like, again.
Displaying information for the operator to check. If the information is correct, the operator instructs the computer to begin the updating process. To see how the updating process works on the complete master file, we'll look at a simplified version. We'll represent it on the left of the screen. And on the right is a transaction file. That's a temporary file containing all the transactions entered during the day. The processing takes place in the working store. We'll represent working store across the center of the screen. We've arranged for the records in both files to be stored in order. The first item to be processed is the first transaction. That has to be joined onto the corresponding master file record. So a copy of the first transaction is brought into the working store.
So you can see how setting this up in a very clever way to take advantage of this limited hardware, which is these tapes, which are always one direction. They set up this is a very humans being super clever and kind of like basing it on things they were already doing, except not with people, not with computers, with machines. They're using people, or they're using a combination of people and machines. And now they did this part, the part that does the rectifying all this stuff. So there's because they had so many errors and mistakes, it was just a big problem. So they clever, because they're already kind of doing it already using people. Now they're going to use the machines, like they can sort things and coordinate things. That's computer science. How you put these things together and situate these things to be the most efficient way possible with the limited hardware that we got with what we're doing. That's computer science.
Next, we want a record from the master file. We start at the beginning of the file and copy the first record into the working store.
I mean, they could have easily done the thing where we're going to change the records on the tape. Do you know how hard that is? That's super hard. That's really hard. They could have done it, but instead they did it this way for good reasons. Like, you always have the record of the old thing. Nothing gets destroyed. If you mess up a job, you can just rerun it again with the old data. There's all these reasons why, and it comes up again when you do parallel processing, which we'll talk about, and just a style of programming which can eliminate a whole class of bugs is doing this style. It went out of vogue because it takes time to copy everything. Then they just said, no, we're just going to go right into it and change it. And they was like, oh no, that's a bad idea. And they went back to the style. It's so these cycles like in a spiral.
Here, the transaction in working store is for the same account as the master file record.
Techniques.
The computer can test this by checking that the identifying numbers match. So the new transaction details are added onto the record.
Right, these two match. So it's like, oh, okay.
And now the updated record
Add that
can be used
one.
to start a new version of the master file. That's the story for the first transaction. Now, the next transaction can be processed.
These is why they have to be in order.
And also copy the next master file record. But this time there's a difference. The transaction isn't for this account. The identifying numbers don't match, so this record isn't changed. It's copied directly onto the new master file.
So this is why the sorting thing became a big deal, because you had to have these things in order. And they didn't really, and so doing a sorting thing by hand was a real pain in the neck. So there was a whole process they would go through to make sure all these things are sorted on one tape, making copies, before they would start this process. So they could literally go down the process, just like if it was a person doing it. They would stack the papers in all in the order, so they would make sure everything's done efficiently, and by the time they're done, they know everything's been finished.
The same thing happens with the third master file record. It goes into the working store. It doesn't match. Now for the fourth record. Into the working store. And this time it does match. So the new transaction is added onto the record. And the updated record is copied to the new file. And so it continues until all the records have been processed, making a completely new master file. This method, taking transaction records one at a time and working through the master file in sequence, is a standard technique for processing a sequential file at high speed.
On average, the computer can process about 70 records every second. To achieve this...
Ooh, 70 a second? Ooh, hold on to your hats, guys. 70 a second. Now we can do like 70 billion a second. All this hardware is in a museum or junk pile somewhere.
The transaction file must therefore be in the correct sequence. But transactions arrive at the computer center from our branches in random order. Also, we have a great many transactions arriving from other sources. For example, yesterday, we had to process about 175,000 checks which had been presented for payment at other banks. So what we do is we store all these transactions on magnetic disks, just like this. And then, at about 5 p.m., after the collection process is ended for the day, but before we start the master file updating run, we have to get all these transactions sorted into account number sequence.
So they got to sort it. So they use a hard disk here to sort it. Now, the reason why why didn't they just use a hard disk for all of it? Because they're freaking expensive. You could for all these tape systems back here. All these tape systems were probably just one of these at the time. So they were like trying to work within budgets. This is still a multi-million-dollar installation. This is probably $500,000, $1 million or more. And each one of these tape drives is like $100,000.
So what we do is we take all the transactions from the various disks, we sort them, and then store them in a single disk bag. And this is the disk we use for the updating run.
This is where that sorting thing, can we make this go faster? We got too many. We have to buy another system to do the sorting, to do it in parallel. We have to figure out that. So the quick sort came and saved their asses, actually.
That's another feature of batch processing. If the transaction records were in a random order, like this, then the computer would waste time going backwards and forwards to find records that matched.
Random access.
So instead,
you can't do that with tapes. It's super hard. For the tape to do the random access, you actually have to rewind it all the way back to the beginning and then go every little piece along the way, and then go all the way back to being long. So it's super slow.
The transaction file is sorted into the correct sequence. Then it's easy to work through the two files, record by record.
Right, so the sorting. He just like skipped over a big problem of sorting all that stuff. It was a big problem where they had.
With this technique, we just start at the beginning of each
They figured it out though.
file and work our way through to the end, reading each record only once. That's the essence of batch processing. We can summarize what's happened in a system diagram, which shows that transactions are first collected on several disks. At this stage, the transaction data is in random order. Next, it's sorted.
So these are on these random access platters. This is the most expensive stuff. So, because, yeah, that's just how it goes.
And combined on a single disk. This disk is used to update the master file held on magnetic tapes. The updating process creates a new version of the master file. And it also produces a large amount of printed output. Much of this printout consists of statements for bank's customers. Blank statement forms are fed into a line printer, and it prints information about each account onto the forms. Then the statements are sent off to the branches, but getting them there can cause problems, as Norman Irvin explains.
Each night we have to send reports and statements to our branches to arrive the following morning. For branches in the Edinburgh area, there's no problem at all. However, we do have a problem, for example, in the case of Kirkwall in the Orkneys, where the output has to be dispatched by 8:30 p.m. in the evening to arrive in Kirkwall the following morning. But of course, the updating process is seldom completed before 11 p.m. each night. So we get around this problem by taking advantage of the fact that the master file is contained in 22 separate magnetic tapes. And we simply arrange for those branches furthest away from the computer center to have their accounts on the first tapes to be processed. In this way, we can produce our output reports in 22 separate batches according to the geographical location of the branches.
So isn't that clever? They're like, oh, the furthest ones away, we just do those first. This all got wiped out with telecommunications right after this video ad. Right after they edited this video, this branch got converted to telecommunications computer.
This batch processing operation.
Not couriers to branches from the output. They just put it on the phone line, right? That's why that basic stuff where people's eyes went like this. Boah, you mean I can communicate I don't have to be right there doing couriers to that? No, you can just do it over a phone line, have the printer up there. Oh.
Happens every night, 22 times, once for each tape in the master file. And each tape is updated by copying. Is all this copying really necessary?
You might think it's a waste of time to copy the records on our master file every...
Yeah, and that's what they talk about this, like when you're talking about the mutable style of programming, when they're like, you're copying everything, why don't you just change it, blip, 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 blip. Yes, you can. But the problem with the blip, blip, blip changing is when you have parallel processing, they can get a little confused. So if you just copy everything, which happens super fast now, back then it took some time, but now it's super fast, then all that, you can do parallel processing of all kinds of stuff and nothing gets messed up. That's why.
Every night. But we think this is the most cost-effective way of doing things. And remember also, as a bank, we really are obliged to balance our books every night, down to the last penny. And this can be quite easily done as we produce the new master file each night. And when we complete the updating process, we don't throw away the old master file. For data security reasons, we keep several generations of our master file, so that if today, for example, we have some damage to our master file, we simply reconstruct the information from yesterday's master file.
Yeah. And that's one of the things also about immutable programming is you have the ability to reconstruct the whole chain. Yep.
And that's a bonus from batch processing, because every day a new master file is created. The previous version of the file is simply stored away. But next day, the new master file must itself be updated. This means it becomes the input.
And they got a whole bunch of them.
And the output is yet another new master file. And so it goes on, day after day. Each newly created master file is the file which has to be updated the following day.
Yeah, so go watch that again if you want to understand batch processing, but that's the big deal. So that was the changeover that happened. And we'll get into the style that was inherited from the procedural. And it's kind of like it's the first style you would probably naively do anyway, given that you were coming from this assembly language level stuff. So we'll get into that on the next episode. Give me a like and subscribe. I'll talk to you soon.